In this video, I want to continue the discussion about comparing two population means. In a prior video, we saw that we're trying to learn about the relationship. Which mean is bigger? We're not specifically interested in mu1 or mu2, but we really want to compare the two means. And the tools that we have to work with are just confidence intervals and test hypothesis, the same thing we've seen before. So we can do a confidence interval for the difference between the means. We can do a test hypothesis. We've talked about how there are two different types of analyses. Again, in a prior lecture, I've talked about independent sampling, where we randomly and independently sample from two target populations. In this video, I want to talk about a paired difference analysis. There's some other names that we can use, a matched pairs design or a matched pairs analysis, or dependent samples. Here, pairs of observations are going to be linked together. So we're going to pair observations together and analyze the differences between the pairs of data. Look at this, dependent sampling. The data collected is linked by some common pairing variable, and the paired differences are calculated and are analyzed. What's interesting to me, and it's not overly interesting to many people, but what's interesting to me, if you take a look at the calculations we're going to do, and again, when I say we let the computer do most of the math for us, but when we take a look at the calculations, it's exactly the same as the one population analyses, the confidence interval and the test hypothesis. So the way the calculations are done, it's like we're doing a confidence interval for a single mean. It's a paired mean now, but it's a confidence interval for a single mean, or a test hypothesis for a single mean. So the calculations are the same as if you're working with one mean, but the interpretations are identical to the two population independent comparison that we just got finished looking with. So to me, it's kind of a quirky little cool analysis because it puts together a lot of the things we've seen over the last little bit. Now, here's how the data is compared. And an example I tend to use, let's say I want to compare two different brands of razors, and I'm trying to figure out which one is a better razor. And so I might ask some people to give me some kind of some feedback, to, maybe on a 10-point scale, where 1, I hated that razor, to 10, I loved that razor. Now, the independent random sample would say, let's go get a group of people and randomly sample some and give them the first razor and say, hey, you know what, go and shave and come on back and tell me what you think, 1 to 10. And then we'd take another random sample, and for the folks that were left, we'd give them razor 2. Now, what could happen, okay, just bear with me because I'm going to make this an extreme example. Suppose that by some just crazy, weird luck, everybody in the first sample loved to shave, and everybody in the second sample hated to shave. Okay, now imagine if you will. So when I give folks in sample 1, the love to shave group, razor 1, or the first brand, they're going to love it. Not necessarily because razor 1 or brand 1 is outstanding. It's those people are weird. They like to shave. Likewise, if the second group of people hate to shave, it really doesn't matter what razor you give them, they're going to hate it. And so if that were the case, if there was this shaving bias in the two different, or between the two different samples, then you're not really going to learn about which razor is better. You're just going to learn that one group of people like to shave better than the other. And that's what the dependent sampling is hoping to avoid. Now, I should say this. In the random sampling that we do, we hope to randomly get rid of any biases like that. However, if there's another way to collect the data, we should pursue it. And so in the dependent sampling, what we're going to say is, rather than give one group of people razor 1 and one group of people razor 2, we're going to give each person 1, is going to get razor 1 and razor 2 and tell me what they think. So they may love to shave, so they're naturally going to be inclined to think, wow, my razor was great, but maybe they like razor 1 better. So maybe on a 10-point scale, they said this was a 9 and this was an 8. And so both those numbers are really high. They like both the razors, but they like this one, the first one, a little bit better. Let's say person 2 hated to shave, just loathed it, couldn't stand it. So when they give ratings, they get this bias against shaving. So maybe they say, oh, well, razor 1's only a 3. That wasn't a good experience at all. Razor 2 is a 2. And so it's a little bit better way of collecting the data, because that razor, that shaving bias, let's say it that way, whether they like to shave or whether they hated to shave, is kind of factored out, because we're not going to look at the 9 and the 3 and the 8 and the 2. What we're going to do is we're going to create the difference between both of those numbers for both pairs, and we're going to be looking at the ones. 9 minus 8 is 1, 3 minus 2 is 1, and we do this for n pairs. Number of pairs, the number of differences, that's an n sub d. And so what we really look at is the column of differences, and we end up with n of them, n sub d. We look at the average of the differences, which we call d bar, and we take a look at the standard deviation of the differences, which is s sub d. And so you end up with an average, a standard deviation, and a sample size. And so you end up working with the same values we worked with before. When we worked with a single population mean, we called this x bar, we called this s, and we called this n. And we did a confidence interval and a test hypothesis. Like I said, the calculations that we're going to see here, I've actually lobbied the author of the textbook to work with the symbol x bar sub d. So far, he has been resistant to do that, but if you saw it as x bar sub d, just subscript this stuff with d's and it would work. Anyway, that's how the data is collected. So if you know that there's a reason to pair, for instance, let's say you have a new brand of tire and automobile tire, and you're trying to figure out which brand works better, and you got these two brands. For now, I can only talk about comparing two brands. So we'll compare Michelin's to Goodyear's. Is there a way to compare 3 or more brands of tires? Yeah, it's called a completely randomized design, or a randomized block design. There's a couple different ways of doing it, but we can compare 2 or 3 or more means. That's just usually advanced. We're in this class, we look at working with a single mean, we look at comparing 2 means. And so if I had these 2 different brands of tires, rather than put one brand on one car and another brand on another, on the first car, why don't I put both brands of tires? And we'll get some kind of measurement for each brand. And then the second car, we'll put both brands, because the weight of the cars might be different, or the type of driving they do might be different, or the driver itself might be different. Maybe someone's really, they squeal the brakes, they brake real suddenly, or they accelerate real fast. All those things that would cause variation in the data can be controlled by the pairing, and that's an advantage, and we'll talk about that in a little bit. So anyway, here's how the data is collected. Now let's talk the confidence interval. And I said the calculations are going to look similar to us. You remember seeing this before? If you thought about x bar plus or minus z alpha over 2 times sigma over the square root of n, that's our confidence interval for a population mean. Now it's a paired mean, and typically when we're working with a paired analysis, we think of this as the mean of the differences, mu sub d. And so that's the formula you're going to use. The sample size is large, we're going to use a z-value. If the sample size is small, what do you think I'm going to change that to? Sure, it's a t, right? What's a large sample? Well, before we've said, when we're working with means, that a large sample is n greater than or equal to 30. Now it would be n sub d, the number of pairs greater than or equal to 30. If you use a t distribution, you're going to use not n minus 1, it'd be n sub d minus 1 degrees of freedom. You should be able to find values like this from the table, from the z table or the t table. You should know which is the appropriate table to use, but ultimately you're going to get 2 numbers on a printout. And while we talk about mu sub d, I think in interpretations, let's think about this as being the difference, a confidence interval for the difference between 2 means. And you've seen this notes before because they're exactly the same. When we go to interpret this result, we're going to do it exactly the same way that we did as when we had independent samples. If the means are the same, the difference between them would be 0. And so it's what's the value 0? What's it related? How's it related to this endpoint? Is it inside? Is it above? Is it below? We have 3 different interpretations to consider. And it's not the numbers themselves, it's the endpoints. If we have an interval, say let's say we had an interval that went from 10 to 20. This doesn't really tell me anything about mu1 or mu2. It's talking about the difference between them. It's telling me that mu1 is anywhere from 10 to 20 units bigger. Why bigger? Because they're both positive numbers. And so when you end up with 2 positive numbers, 2 positive endpoints, the entire interval's above 0. Think about where this value 0 would be. Wouldn't it be over here, below the interval? So if I ask, is mu1 minus mu2 equal to 0? In other words, are the means the same? We'd say we're 95% confident mu1 is bigger than mu2. In fact, we could say mu1 is anywhere from 10 to 20 units bigger than mu2. Typically when we're comparing means, and I'll say the same thing when we compare proportions in a future video, typically we say that mu1 is just bigger than mu2. We don't care by how much. Typically, we're just interested in learning which one's bigger, which battery lasts longer, which tire brand lasts longer, which razor is preferred more. We usually don't say, oh, it's anywhere from 0.17 to 1.2 rating points bigger. We just say, hey, razor 1 is preferred over razor 2. If you have an interval that's entirely negative, if we have a negative, in this case, let me change the numbers to negative 20 and say, let's say negative 15, just to use different numbers. If that's the confidence interval, then 0 is on the upper side. Do you think the means are equal? No, I don't, because 0 is not in the interval. I'm 95% confident mu1 is less than mu2. And in this case, let's say mu1 is anywhere from 15 to 20 units less than mu2. And what if we end up with something like this? An interval goes from negative 8 to positive 7. Well, where's 0 now? Inside the interval. And so we're not going to say, yes, we believe mu1 is equal to mu2, but we're saying it might. We cannot determine which mean is bigger. The means might be the same at the 95% confidence level. So as you've heard me say in the past, it's the signs, whether you have positive signs or negative signs on the endpoints. That's how we make our interpretations when we're comparing means, whether we're doing independent comparisons from a prior lecture or the paired or dependent means now. We're going to look at the signs to try to help us interpret the confidence interval results. A test of hypothesis. And again, we can think of this as mu sub d or the difference between two means, mu1 minus mu2. I don't really care how you think about it. Typically with a test, we'll write it this way. The difference between the means, and I'll write it as the mean of the differences, mu sub d, it's equal to d naught. The d naught value is usually 0. And I don't know why I'm using a mu there. That's kind of funny. It's usually the value 0. And if you think of it as being 0, what the null hypothesis is saying is that the population means are the same. And the alternative saying, no, it's not. And it might say less than, it might say greater than. It depends which one you're trying to say is bigger. If you're trying to say the first one's bigger than the second one, we're going to do a greater than sign there. Listen to the wording very carefully here. If you're saying the second one is bigger than the first one, you heard the word bigger, didn't you? The second one is bigger than the first one would actually be a less than test. One-tailed tests, when we're comparing means, or comparing proportions for that matter, get a little tricky with the direction of the test, because I can use the word bigger than or exceeds and it be a less than test. If I want to see if the second one exceeds the first, that's a less than test. If I want to see if the first one is less than the second one, well, that's a less than test too. So it depends how you look at it. You got to be real careful with the one-tailed tests. The test statistic, we've seen this before. X bar minus mu naught divided by sigma over the square root of n. It's the same thing we've seen before. It's a number on a printout. You're not going to have to do this math. I'm going to call it a z distribution, or I'll use a z symbol if we're working with a large sample, n sub d is greater than or equal to 30, or I'll use a t-test if it's less than 30. Here in your notes, I'm only saying a p-value. There's a rejection region option, but I want to get you leaning more towards p-values now. The computer will do most of the work for the p-values. It'll calculate the p-value, and you need to be able to interpret it. The p-value on the printout, you got to be careful, right? Because if I give you a p-value for a not equal to test, but I really want to do a one-tailed test, that's not the right p-value to use. Likewise, if I give you a one-tailed p-value, but I want to do a two-tailed test, you got some work to do. So the computer's going to give us a number. It's your responsibility to make sure that number is correct, and then you need to be able to interpret it. And unfortunately, the interpretations here are pretty straightforward. If alpha is greater than the p-value, we're going to be able to reject H naught. If p is low, reject the ho. You've heard me say it before. You will hear me say it again. I was out today, and I was talking to some people, and they said, oh, I remember when you said when p is low, reject the ho. Is that something that's really true? And I was like, yeah, it is. And they had me a long time ago, and that's what they remembered. It always works. If p is high, we fail to reject the null hypothesis. That's how we make conclusions in a test of hypothesis. And so the goal now is to take a look at how this works. So to test how it works, we can take a look at an example. Before we do that, oh, I missed this page of notes. Sorry about that. There's two assumptions for this analysis, and really there's four assumptions that you guys have to be familiar with at this part of the semester. There is random, there is independent samples, there is approximate normal populations, and there's equal variances. And you gotta kind of work your way through this. And I'm going to try to continue to build on this theme to help you work with assumptions. The random part is the easiest part because everything we do requires a random assumption, a random sample. In the independent comparisons, we needed 2 random samples. Here we need a random sample of paired differences. So if I'm working with the razors and I'm working with people, I need a random sample of people. If I'm working with automobiles and I want to compare tires on the automobiles, I need a random sample of automobiles. I don't want to just get one automobile that's more beneficial to one of the brands than another. I want just a random sample. So there's always a random sample of paired differences that are needed. The independent assumption is not needed here. In fact, it's incorrect. We're pairing data together. So when I look at the tires on one vehicle, brand A tire on one vehicle, I'm looking at brand B. What's it got in common? It's got the same automobile. They are not independent. They are definitely dependent. So this analysis is always going to require a random sample pair differences, and it's never going to have an independent assumption. Approximately normal, whoops, let's do that. Approximately normal might be necessary. When do you think we would need approximately normal? Well, if our sample size is small. If n sub d is less than 30, we're going to need the population of paired differences to be approximately normal. If n sub d is greater than or equal to 30, we don't need that because of the central limit theorem. So this one requires some thought. Equal variances doesn't make sense because, as I mentioned, when we're working with the paired analysis, the calculations are like a one population problem. There's only one variance. It's a variation of the paired differences. There aren't 2 different variances, so you're never going to need the equal variance assumption here. So random, yes. Independent, no. Equal variances, no. Approximately normal population of paired differences, maybe. It's a thought. You gotta think your way through it. There's a thought process. But if you understand kind of the logic behind each of those assumptions, hopefully you'll be able to figure it out. And then the last part of this video, and then I'll pause, I'll stop it and we'll pick up another one with some examples. What's the advantage? Why are we doing this? Well, it's what I mentioned earlier. If I know that tires are going to wear differently from one automobile to the next or from one driver to the next, pairing on the automobile and the driver would be a good idea. If I know some people love to shave and other people hate to shave, pairing on a person and giving them one of each razor. It's going to take that unknown variation, that unknown variable, like or dislike of shaving, the weight of the vehicle. Imagine, if you will, real heavy, like giant SUV, maybe like a suburban type of SUV, a big, heavy automobile, and then something that's really, really kind of light, something like my wife drives a Mazda Miata. Which automobile do you think is going to be rougher on the tires? Do you think the really light Miata or the really heavy Suburban is going to wear tires more or harsher? Well, of course, the heavier vehicle is going to wear the tires more than the light vehicle. And so by putting some of the brand of both brands on the heavy vehicle and some on the lighter variable, we're taking that vehicle weight size out of the equation. It generally, when we pair like that, it generally allows us to better detect differences in means when they exist. That's what we're trying to do, right? We're trying to figure out, are the means, what's the relationship, what's our goal? To determine what the relationship is of the population means. If there's one technique, one sampling technique that gives us a better shot at doing that, we should use that. If pairing the data gives us a better chance of determining if one of the tire brands is better, we should definitely pair. We should definitely pair when it's appropriate. So if you start looking at an analysis, you're like, I want to compare these 2 means, but I know this affects it. I know that if we consider this variable, it's pair on that variable. Try to come up with some way of collecting the data so that you give yourself the best chance of finding differences in the means. If the means really differ, if one of the tire brands is really better, we want to try to detect that. We want to come up with a way of collecting data that gives us the best chance. And this last statement here usually allows us to better detect it. It's called the power of the test. The power of the test refers to, are we able to detect the differences in the means if one really exists? And so that's our goal. We're trying to find out when means are different. So let's give ourselves, in terms of the independent or dependent, let's give ourselves the best chance of detecting those differences that we can. And that's why we like paired difference analysis. And as I mentioned, we're looking at comparing two means. There is a paired analysis. It's called a randomized block design for if you were comparing three or more. So an example of automobile tires, 4 would be a perfect number, right? If you think about an automobile, there's 4 tires. We could compare 4 brands. And so for each of the cars that were randomly selected, we could put one of 4 tire brands on each of the tires, and we would be able to compare the mean life, how long the tires last of 4 different brands of tires. Be the best way to collect the data. Anyway, I'm at about 20 minutes, so I'm going to cut the video off now. That's our introduction to the paired difference analysis, or the dependent samples or matched pairs. I'm going to use those terms interchangeably. The next step is to take a look at some examples and then show you how to generate a statistics printout for those types of analyses. So I'll come back and do that in different videos. So long.